In this video, we're going to take a look at non-homogeneous linear recurrence relations. At this point, we should be very familiar with recurrence relations, but to this point, we've only looked at homogeneous linear recurrence relations. So now we're going to take a look at a non-homogeneous, which essentially just means that that f of n is not equal to 0. So up to this point, we've looked at situations like this, where we have some value based on some constant multiplied by a previous value. Now, if you'll notice, we have this extra function of n. Previously, we did not have a function of n, and that's what made it homogeneous. Now it's non-homogeneous because we do have a function of n. Now, we can find values in the sequence just as we did before. So obviously, we're given that a1 is 3. And to find a2, I'm just going to use the recurrence relation. So a2 is 3 times the previous value, which is 3, plus 2 times n, which in this case is 2. So that would give me 9 plus 4, which is 13. And I could continue that process and find the values, but this is not quite as easy as how it was previously because we have this other function. So what we want to do is we want to learn how can we solve it. In the same way that we solved the homogeneous recurrence relations to find an explicit function, we want to do the same thing here. And to do that, one of the steps has to do with what we call the associated homogeneous recurrence relation. So if I take out the function and just look at everything else, that's the associated homogeneous recurrence relation. So there's two main steps for solving the non-homogeneous linear recurrence relation. And the first is to solve the associated homogeneous recurrence relation, which actually is two separate steps, which will make sense when we look at an example. But we're going to denote that A and H. So again, we're going to solve just like we've done to this point. So if you haven't watched the previous videos, then you must watch those first because that's going to be how we solve this first part. In addition, we have to solve for the particular solution, and the particular solution is going to go back to those initial values that are given to us. We're going to denote that A and P, and for that step, this is going to be our new step, what we don't know how to do yet. We're going to basically have to guess the form of A and P, and so I've made this table for you. And before I talk about the table, I do want to point out that your book, first of all, doesn't have a table. But if you look at other textbooks or other videos, you might see this written as A sub 0, A sub 0, A sub 1. You might see this written as alpha, and then alpha, beta. You might see it alpha 1, alpha 2. So I guess what I'm trying to say is it doesn't matter what variables you use. This is saying if your function is a constant, then that's going to be the form of your particular solution. If your function is n, or something times n, you're going to have c of n plus d. It's going to be linear. If you have something that's a quadratic, you're going to have cn squared plus dn plus e. And again, this could be alpha 1, alpha 2, alpha 3, however you choose to write it. If you have some value to the nth power, then you're going to have a constant times some value to the nth power. And again, this probably doesn't make any sense yet, and that's perfectly fine because it will make sense once we actually go through an example. But what we're going to do then to find our final solution, our explicit form of our non-homogeneous linear recurrence relation, is to add those two values together. So let's take a look at our first example, and most of this will make a lot more sense to you. Let's take a look at our first example. So what we're going to do is we're going to find the solutions of the recurrence relation. And just up in the corner over here, I'm just going to remind us that in order to find the solution, I'm looking for A and H and A and P. So I'm looking for the homogeneous and the particular solution. I'm going to start by looking at the homogeneous solution. And so that's going to use just the homogeneous, the associated homogeneous recurrence relation. So how am I going to solve that? Well, I'm going to solve that the same way we did in the previous video. So if you haven't watched video 8.2.1, 8.2.2, 8.2.3. I'm going to assume that you have, because that's the process that we're going to solve. So I'm going to write a sub n. I'm going to write it on the same side, so I'm going to subtract the 3a sub n minus 1 from each side, set it equal to 0, write the characteristic equation, find the roots. When I'm done with that, I'm going to then write that a and h is equal to, remember with my root was 3, I said a times 3 to the n. Typically I had 2 or 3 roots, and so I would have a 2, so I would add b, 2 to the n, but that's not what I have here. I just have the one root. Now, two things I want to point out. First of all, we don't know the value of a, and we can't know the value of a yet. The second thing I want to point out is that your textbook uses alpha instead of a. So if that makes more sense to you, go at it. I chose to stick with a because that's the variable that I used in the 3 previous videos to this video. So here's where I have to stop right now for a and h. So I do have to solve for a eventually, but I don't have what I need yet to be able to do that. Now what I'm going to do is I'm going to look at the particular solution. So I'm going to take the whole recurrence relation and solve. Now before we get started, I do want to talk about the fact that I need a guess. Remember we talked about guessing the format of the non-homogeneous function of n that is part of our recurrence relation. So if I look just specifically at this function, that's just a linear function. And remember that my guess should have been that a n p is equal to cn plus d, or you might see that as a0n plus a1, or whatever variables, you know, make your heart beat faster. So that's my guess, and the reason that that guess is important is because every time now that I see a sub n, I'm going to replace it with cn plus d. So let's take a look at my recurrence relation. I have a sub n is equal, actually I'm going to go ahead and in this step move that 3 a sub n minus 1 over. And now some people like to write it as equal to 2n. I'm sort of partial to having it set equal to 0, so I'm going to go ahead and subtract the 2n as well. Either way is perfectly valid. This is the way that I'm going to choose to do it. So what I'm going to do is every time now that I see a sub n, I'm going to replace it with cn plus d. So a sub n is now going to be cn plus d. And then I keep my 3, and then a sub n minus 1 is going to be cn plus d, but instead of n, I'm going to use n minus 1. So that's going to be c times the quantity of n minus 1 plus d. And then of course I have minus 2n equals 0. And now this is just algebra, so let's just do some simplification. cn plus d, I'm going to distribute the 3 and the c to the n and the 1. So c times n is cn times negative 3. Negative 3 times c times negative 1 is plus 3c. Negative 3 times plus d is minus 3d, and then of course I have minus 2n. Now what I want to do is I want to sort of write it in this format so that I have all of the values that include n together and all of the ones that don't together. So this is cn, which is 1cn and minus 3cn. Those will combine to be negative 2cn. And then I've got minus 2n. And then I'm going to write all of the values that don't have an n. So I have plus d and minus 3d, so that's negative 2d, and then plus 3c equals 0. So we're almost there for the c's and the d's. I'm going to go ahead and distribute or factor a 2n, a negative 2n, and that leaves me with c plus 1. And then I'm going to really just write this as negative 2d plus 3c. Now, this isn't really the zero product property. Obviously, if I was using the zero product property, it would have to be a product, and this is a sum. But what I'm trying to do is determine values of C and D where this would be a true equation. So where this does in fact equal 0. So how do I do that? Well, I know that if C plus 1 is 0, then this whole value is 0. And if this whole value is 0, I'm basically going to add 0 plus 0. So essentially, it's like the zero product property. I'm going to take C plus 1 and set it equal to 0 and find that C is negative 1. And I'm going to take negative 2D plus 3C and set it equal to 0. And I'm going to replace C with the negative 1 that I just found. So minus 3C, I'm sorry, minus 3. And solve, so I'm going to add 3 to each side and then divide by negative 2. Sorry, that's a negative 3/2. So now what? I've solved for C, I've solved for D, but I still don't have a solution. What am I supposed to do? Well, now I have to go back up to this original format. A sub n. I'm going to replace a and h with a, 3 to the n. And what, in fact, is a and p? Well, let's take a look. A and p, let me find a color that's not overused. A and p is cn, so that's negative n, and then plus d, so plus negative 3/2. So this, it's what's going to be substituted in for a and p. So I've got negative n, so I'm just going to get rid of the plus, minus n minus 3/2. We are almost there, I promise. So what's going to happen now is now I have to figure out what is a, because that's the only value that I have left to solve for. So this is where I'm going to have to use that initial condition. So I'm going to say A1 is equal to 3, and 3 is going to equal A times 3 to the first, because n is 1, minus n is 1, minus 3/2. So I have 3 is equal to a times 3 to the first, so 3a. And then I'm going to combine these two together, so that's minus 1 or minus 2/2. So this is minus 5/2. Add 5/2 to each side. So again, 3 is kind of like 6/2, right? So if I add 5/2 to each side, I get 11/2 is equal to 3a. Dividing by 3, I get 11/6 is equal to a. So finally, what is our solution? Our solution is this format. I've got a sub n is equal to, and instead of a, I now have 11/6. So basically I'm looking at what we did here. So this is 11/6 times 3 to the n, and then minus n minus 3/2. Woo, that was a lot of work. But the real question is, did we do it right? So we did previously find some values of that recurrence relation without using the explicit function. So let's just compare. Let's take a look at a sub 2. A sub 2, according to my explicit function, says take 11/6 times 3 squared minus 2 minus 3/2. So 11/6 times 9 would give me, let's do 11/6 times 9 over 1. I'm going to go ahead and combine these two together. So this is 4/2 minus 3/2, which is 7/2. Over here, the 9 and the 6 would reduce, so that's going to give me 2 here and 3 here. So this is 33 halves minus 7 halves, which is 26 halves, or 13. And if you'll recall, 13 was a sub 2. So you can check as many values as you would like. I'm going to stop there because I've already spent like 11 minutes on this question. So that is the solution. And again, this is for values n greater than or equal to 1. We're going to take a look at one more example. Again, only one, because these questions take quite a while. So again, this video will go past 20 minutes, and I apologize for that. But let's go ahead and get cracking on this one. Just keep in mind, same process, A and H plus A and P. And this is the associated homogeneous recurrence relation, and obviously this is the part of the function that makes it non-homogeneous. So when I get started, I'm going to, let's just box that in a different color. I'm going to start with A and H, and to do that, I'm going to take an minus 2, an minus 1 is equal to 0. Write the characteristic equation, find the root, and write that ANH is going to be equal to A times 2 to the n. Again, your textbook would show that as alpha times 2 to the n. Now let's take a look at the non-homogeneous portion of it, or the function that makes it non-homogeneous. Just as I did before, I have to think about what my guess is. So going back to that table, if I'm looking at Rn, my guess should be CRn, so that's what we're going to use, is C times 2 to the n. Exactly like this. Now, as I'm then rewriting my function, an minus 2, an minus 1, minus 2 to the n is equal to 0, and I'm going to replace a sub n with c times 2 to the n, I do want to point something out. Just as this is something times 2 to the n, and this is something times 2 to the n, and this is 2 to the n, we can see that we're going to have a multiple root here. So just as we did before, if I would have had a multiple root of 2, I would have had bn 2 to the n. That's exactly what I'm going to do here. So what I'm going to do here is instead replace a sub n, I'm going to write as cn 2 to the n. So I'm going to write an n up here to remind me. And then 2, and then this is a sub n minus 1, so this is going to be cn minus 1, 2 to the n minus 1, and then minus 2 to the n is equal to 0. So again, now this is the algebra part. We're just going to do some simplification. This first term stays the same. My second term, I have minus 2, well, let's just get these 2's together. So here I've got a 2 and a 2 to the n minus 1. So total, that's 2 to the n. And then I have times cn minus c, and then minus 2 to the n. So obviously, distributing that 2 to the n, I have cn 2 to the n, and then minus 2 to the n times minus c gives me plus c 2 to the n. Minus 2 to the n is equal to 0. These two are exactly the same. One is plus 1, one's minus 1. So that leaves me with c 2 to the n minus 2 to the n is equal to 0. Or if I take out the 2 to the n, c minus 1 is equal to 0. And that gives me, if I set c minus 1 equal to 0, c must be equal to 1. So now I'm going to go back to that function, and I'm going to replace what I have so far. So I'm going to replace the homogeneous solution with a times 2 to the n. I'm going to replace the particular solution with n, well, c is 1, right? So this is 1 times 2 to the n times n. So n 2 to the n. Now I'm going to use the initial condition that a sub 0 is equal to 1, which obviously I have forgotten to write on this page, and I apologize, but a sub 0 is going to be equal to 1. That's my initial condition. So from here, then, I'm going to write a sub 0 is equal to a times 2 to the 0 plus n, which is 0, times 2 to the 0. A sub 0, which is equal to 1. So 1 is equal to a times 1, and then plus, that's obviously 0. So a is equal to 1. So what is my solution? My solution is a sub n is equal to 1 times 2 to the n, so that's 2 to the n, plus n, 2 to the n, which obviously I can also write if I factor out the 2 to the n, that just gives me 1 plus n. And I will leave those checks to you to verify that these in fact do work, but obviously I've checked it before I made this video and they do in fact work. So I apologize for leaving out that initial condition, but this is the correct solution for that non-homogeneous recurrence relation. Coming up next, we have several videos to get us ready for how to use generating functions. The very next video deals with modeling word problems or real-life applications with generating functions.